Welcome to this lesson on C file operations. To store data between one user session and another, programmers often write data out to a file. In this lesson, you'll learn how to read and write files from your C programs. You'll also learn how to rename files, delete files, and perform just essential file operations that you would need to store data from one time that user starts the application until the next. So let's go ahead and get started. In general, to perform a file operation requires 3 steps. First, we declare a file pointer. We're going to use the type file, and we'll create a pointer to it so you can see that we've got the file keyword, and then we've got a FP, which is our file pointer. To open a file, we use the C standard library fopen. We'll pass it the file name and the mode that we want to use to open the file, such as read-only for write access, or read or write access. The most common are read and write, and we'll see later that we can open a file in binary mode, which is important when we start to store structures and other data types to our file. Then we'll perform the file operation. The 2 most common routines that we use are fgoods, which gets a buffer, essentially reads a line or reads a set of bytes from the file. So we specify the size of our buffer, and we specify the file pointer. The file pointer keeps track of where we're at within the file. So if we're reading through a file, each time we read data, behind the scenes, the file pointer gets updated to point to the next data that we'll need to read. The fputs function writes a buffer to a file. And when we're done with our file operations, we need to close the file, and we do that using fclose. So let's look at a simple example. The file that we're using, our data type, is defined in standard.io.h. So we include standard.io.h at the top of our program. Int main void is no different than what we've been using. So our first step, declare the file pointer and open the file. And so you see that we're opening a file called output.txt, and we're opening it in write mode. The W says write mode. We then use fputs to write our familiar hello world to the file, and we specify which file we're writing to by using our file pointer that we previously opened. We're done, so we can now close the file using fclose. So let's do just the opposite now. We've just created a file, so let's read what's in that file. Standard.io.h, because we have the file definition within it, int main void. So we open our file, output.txt, the same file, but this time we're opening it in read-only mode, so we pass it the R for the mode. We need to have a variable that we're reading our data from the file into, and so we define a buffer, 256 bytes. It could be 512, it could be 26. It's kind of the trade-off is we don't want it to be so large, but we want it to be large enough that we reduce the number of file operations that we need to perform. So 256 is a pretty good medium. We're going to read the data from the file into the buffer, so we pass the buffer its size, so the fgets routine knows how much data to read, and the file pointer, which specifies which file we're reading from. When the routine ends, printf says the data that we read from the file is %s. And we're using %s because we read a character string buffer, and so we display our data. So in this case, if we run this program, let's actually run both of them. So let's go ahead and create our file and write data to it. The program runs, we don't see anything on the screen, and that makes sense because we're writing to a file. We didn't write anything to the screen with printf. Now we've got our second program, and it's going to open that file we just created and display its contents. And sure enough, the data that we read from the file is hello world. So everything's looking good. We've created a file, written to it, closed the file, reopened the file, read from it, and we got the same data. So life's good. In the previous example, we read and wrote a buffer. In our case, it was 256 bytes to a file. Depending on your application, there may be times when you just want to write a character to a file or read a character from a file. In such cases, we can use the fputC function that's built into C, or we can use the fgetC. So we're going to put a character or get a character. So let's look at our first example. We're including string standard io.h. It's got our file definition. We then open a file in write mode called alphabet.txt. We then have a simple loop that's going to loop through the letters of the uppercase alphabet, and as it's going through the loop, it's using the fputC function to write that letter to the file pointer. And remember, the file pointer keeps track of where we're at in the file. So we write a character, it advances to the next location. Write another character, it advances to the next location. So we're going to write the 26 letters of the alphabet, and then when we're done, we're going to close the file. So let's go ahead and run this program. Again, nothing appears on the screen because we didn't use printf to write any messages. All of our output's being written to the file. And so let's do our opposite and go ahead and open the file. Same file, alphabet.txt. We're opening it in read mode this time. We're going to be reading a character at a time, so we define a variable that we're going to read the data into. It's called letter. And this is kind of an interesting loop. And so it says, while letter is assigned the value that's returned by fgetC, and you can see that those are in parentheses, so it's going to do that first, is not equal to the end of file. When fgetC encounters the end of file, it's going to return an EOF. Otherwise, it's going to return the letter that it read. So we're testing, was the letter assigned the end of file? If it was, stop the loop. If it wasn't, use the putchar to output the letter to the screen. And so we're going to do that for every character that's in alphabet.txt. We don't know that there's 26. There could be 5. There could be 1026. We're just going to loop until we find that end of file indicator. When we're done, we're going to close the file. Let's go ahead and run this. And sure enough, we read the 26 letters of the alphabet that we previously wrote to the file. So by now you're very used to the printf function, which writes a formatted string to the screen display. In a similar way, C provides a function called fprintf, which writes a formatted string to a file. And then there's a corollary function, fscanf, which will read a formatted string from a file. And so these can be kind of convenient depending on what you're trying to create. If you're creating a report or something, it's nice to format the output. But it's a little trickier, you'll see, when we try and read the data back in. And so we'll cover both. Let's look at writing formatted output to a string. So in this case, we're including standard io.h. It's got our file definition. And then we're opening a file called sample.txt. We're opening that in write mode because we're going to write output to it. Then we're using fprintf. You can see that the first argument to fprintf is our file pointer, where we want the data written. Then we have our string that specifies our formatting. We're going to be using a string, an integer, and a float. And if we look at the parameters we're passing to fprintf, we're passing a string, an integer, and a float. It looks very much like printf. And so after we write the data to the file, we then close it. Let's go ahead and run this program. Again, the program runs, writes the data to the file. We don't see any output because we're not writing anything to the screen display. And so we're now ready to read that output that we've written back. So let's take a look at a program that uses fscanf to do that. So a very similar program. We're opening the file sample.txt that we just created. This time we're opening it in read mode because we're going to read from it. We're going to be reading variables in, so we need to declare the variables. We have a character string that's 256 bytes. We have an integer called age, and we have the salary variable, which is type float. fscanf is just the opposite of fprintf. It's going to have a specify the file pointer that we're reading from, and our formatted string. We're reading a string, an integer, and a float. And note that because we're passing variables to a function, and we want to change the variable's value, we have to pass the address of the variable to the function. Now you'll remember that by default, C passes arrays by address. So our character array, name, is automatically passed by address when we specify its name. The age and salary variables, however, we have to use the ampersand address operator to pass them by address. And so let's go ahead and run this program. The data read from the file is Chris, age 50, salary 100,000. And so we read the data exactly as we've written it. And so now here's the part that gets a little bit tricky. When fscanf reads data from a file, it uses white space, a space character, a tab character, a new line character, to determine where one field starts and one field ends. And so in this case, we had no white space in any of our output, and so there's nothing to confuse it. We had just the string Chris, we had the integer, and we had the 100,000. But here, things get a little bit more confusing, because look at the name that we're writing out. It's Chris space Jamesa. So we're sticking white space in our file. Let's go ahead and write this to our file. And now we're going to try and read that data back in. And so when fscanf runs, and this is almost the identical code that we just ran, we're reading a string, an integer, and a float. fscanf is going to look through the contents of the file and find that first string, Chris, but then it's going to encounter the white space between Chris and Jamesa and think that that's the next variable. And so when we run this program, we read Chris, but we should have read Chris Jamesa. And look at what it did to our age. That made me pretty old. And my salary just got taken down to 0. And so when you use fscanf and fprintf to print formatted and read formatted input, you need to be aware of white space characters. Otherwise, you're going to get a logic error in your program that looks just like this one. And so typically, you'll use fprintf to print a formatted report. fscanf isn't used as often just because of this white space dilemma that we saw. Now, so far, we've been assuming that every time we try and open a file, the fopen function was successful. We've not been testing. For simplicity, we've not been testing. We didn't want to clear up your code and have you look at test cases instead of the key processing that's going on. But it turns out when fopen cannot open a file, maybe it doesn't exist. Maybe it's locked. Maybe we're trying to open a file that's got a read-only attribute and we're trying to open it in write mode. So fopen can't. When fopen can't, it will return the null value, not a file pointer to it, but rather a null. And so in this case, let's run a simple little program to see if the file sample.txt exists. And so we created the file sample.txt earlier, so it does exist. And so when fopen tries to open it, it's successful, and our file pointer is not equal to null. But if we try and open a file and go ahead and modify this program right now to say mysample.txt, and the file won't exist, and so fopen will return the null value. Every time you open a file within a C program, you should test the value returned by fopen. Make sure it was successfully opened, and we'll see some examples of that later. When you perform file operations, there's going to be times where you'll eventually need to delete a file, or rename a file, or even move a file. And to do those operations, we can use routines that are provided in the standard C library. And so this function is using the remove function to delete the file sample.txt. It's similar to the delete command in MS-DOS or the rm command in Unix. And so it's going to use remove to delete sample.txt. If remove successful, it's going to return the value 0. If it's not successful, it'll give us an error status indicator. So we're going to try to remove, we call the function to remove sample.txt, then we check the status value that was returned. If it's successful, it's 0. So look at, we use the not operator. Remember, C uses the value 0 for false and 1 for true. And so if we get a 0 returned, we can use the not operator to make that a 1, and then we can say the file was successfully deleted. So let's go ahead and run this application. And in this case, it did not delete the file because I'd previously renamed it. Sorry about that. So just as we can use the standard C library to delete a file, we can also use the standard C library to rename a file. And so in this case, we're using the rename function to rename the file output.txt to output.back. Again, rename, if it's successful, returns a 0. If it's not successful, it'll return a status value. And so we can test, if not status, the file was successfully renamed. Otherwise, we had an error renaming the file. And so you can kind of see where we're going with this. In this case, we have a program that does not receive command line arguments. But if we were to pass command line arguments to this program, we suddenly have a pretty valuable utility that can rename the files that we specify when we run the command via the command line arguments. Now, previously, we've written a buffer to a file, we've written a character to a file, but what if we want to write something like a structure to a file? We're going to use the same routines, and the only thing that we're really going to do differently is open the file in binary mode. And that's going to help us eliminate the whitespace problems that we had earlier. So you can see in this case, we create a structure called employee. It's got an employee ID field, employee name field, job title, salary, phone number. We then declare a function that's called store staff, and it receives a pointer to an employee variable. Within that function, we open our file, employee.dat, but we're going to open it for write mode, W, but we're also going to open it in binary. So you can see we put the two together to specify our file mode. We then use the function fwrite to write the worker. You can see that we pass the size of the worker, size of struct employee. We're writing one of them, so that's what the one means. And then we specify our file pointer. After we've written it, we use fclose to close our file. Within main, we create our structure. And so employee ID 1, Chris James, he's a programmer, makes that 100,000, his phone number. And then we call store staff. But we're going to need the address of that variable so we can write it. And so we pass the variable by address. Let's go ahead and run this program. And again, we didn't write anything to the screen, so it just writes it to the file. So we've got a second program that's going to go out and read that data. It again declares the employee structure. It has a function that's called load staff. It's getting a pointer to the structure, and it's going to open a file, employee.dat, the same one. It's opening it in read mode this time, but also in binary, so we're using RB. It's going to use fread instead of fwrite, and so it's going to read the worker. It's passing the size, the number of bytes to read. We're only reading one of them, and here's our file pointer that we're going to be reading from. When we're done reading, we can close the file. Now again, we talked about the fact that every time you open a file, you should test to make sure that it's open. For simplicity, I've not done that here, but if you're writing this test or this code for production, when you get your value back from fopen, you would test to make sure it's not null. When you read the data, you'd make sure that you didn't get an error status. And we'll see how to do some of that here in a minute. We now have a function that's called showEmployee, which just simply writes out the fields of the employee structure. And so our program declares our variable, calls loadStaff to load a value into it from the file, and then it displays what it's read. So let's go ahead and run it. And sure enough, it read employee ID 1, Chris James. He's a programmer, he's got a salary and a phone number. So everything worked. And so this is a great example of how to do binary read and write operations. Again, we need to put our test within the code, which will increase the size of our code and a little bit of clutter, but to make sure that our file operations were successful. And so we've talked about the fact that when we perform file operations, we need to test to make sure that 1, we successfully opened the file, 2, our read operation was successful, or our write operation was successful. And so this program does more testing. And so in this case, we're opening a file called alphabet.txt. We're opening it in read mode. As soon as we do that, we want to make sure that the file was found and we successfully opened it. So we check to see if the file pointer is null. If it was, we display a message, hey, we had an error opening this file, and we return. And notice that we're returning a -1 to the operating system. So if this program is being run from a script, the script can perform conditional processing. Otherwise, if we successfully open the file, we declare a letter variable, and we can declare variables throughout our code. Typically, we have them declared at the top of our code, but we don't need the variable unless we were successful opening the file. And so if we're successful opening the file, we're then going to read one letter at a time. And again, here's our assignment. Note that our letter equals F get C is within parentheses, so we're going to perform that first. So we're going to do the assignment. Then we're going to check to see if the letter that was assigned is the end of file. And so after we read a character, we check, did we have an error? If we did, we say error reading file, and we exit with a -1. Otherwise, we write that letter that we read to the screen display. And when we're done with the file operations, we close the file. And so we talked about the fact that the file pointer keeps track of where we're currently at within a file. We read some data, it advances the file pointer. We write some data, it advances the file pointer. It turns out that the C library provides a function called fseek that we can use to move our file pointer around. We can put it back to the start of the file, we can put it at the end of the file. And so let's look at a program that uses that. Again, sometimes when you're, depending on what your application does, there's going to be times we need to create a temporary file that gets created and then it's deleted when the program executes, and that's done automatically. And so we're going to use the temp file function that's built into the Standard C library to get a file pointer to a temporary file. And so we can write to the file, we can read from the file, and when our program ends, the operating system will delete the file for us. And so in this case, we're opening a temp file. We don't know its name. We don't care about its name. It's just a temporary file. All we need is the file pointer that returns. After we've opened it, we use fputs to write the letters A, B, C, D, E to it, and then the letters F through J to it. We're then using the fseek function to move back to the start of our file. And when we do that, we're going to then read letters of the file that have been written to it. So we should have written the letters A through J to the file. And so when we come back, we're going to, again, note within our while loop, we're doing the assignment, and then we're testing for end of file. We're going to put the characters to the screen. So let's go ahead and run this and see what we get. And sure enough, we get the letters A through J, just as we'd hoped. And so what's this program showing us? One is showing us that we can create a temporary file. If we were to go out and look at our disk right now, there's no file with the letters A, B, C, D, E, F, G, H, I, J, but rather that file was deleted when our program ended. So we opened the temporary file, we wrote to it, then we use fseek to move the value of our file pointer back to the start of the file. Now, what the file contains right now is the letters A through J, so when we do our while loop to loop through the files, we get those letters, and then we're at the end of the file, so F get C returns EOF. That ends our loop, and we close our temporary file. And so what do you got to learn next? We've hinted throughout this lesson that it'd be nice to be able to get to the command line arguments, so we could rename the file that was specified in the command line, or delete the file that was specified in the command line. And so when you run your programs from a system prompt, the command line that you type is gathered by the operating system, and it can pass that command line to our C programs. To allow our programs to access the command line arguments, you can use two parameters within your main function definition. So we can see that our definition of main will change from int main void to suddenly int main int argc and char argv. So we're passing parameters to main, our main program. The first parameter, argc, specifies a count of the number of command line arguments the program received. The second parameter is an array of character string pointers that point to each one of the different command line. And so if we were to execute the command copy source.ext to source.bag, argc would have the value 3. There's 3 parameters on the command line. The first value of the array is going to point to the program that's running. The second one, it would point to our first command line parameter. The third one point to our second command line parameter. And so we can access these within our program and use them. So in the next lesson, we'll learn how to do command line processing. It really starts to open up the door to a lot of functionality. And you think of all the Unix commands or MS-DOS commands that support command line parameters, you're going to learn just how to do that.